All right. Thank you very much. So everyone, thanks for coming. A little bit light, so I hope more folks join us here today. So I'm Carlos Costa. I'm a distinguished engineer at IBM Research. I lead the research strategy for cloud-native AI. I work with a worldwide team actually building technology that goes into a few of our products, things like Watson X and OpenShift AI. So today I'll actually be talking about this platform. It's broader, includes Ray and a few other things, and I'll take you guys through what it looks, right, and our journey building this platform. So there are three parts to this section. So one, I'll start with like what it takes, okay? And of course, foundation model is a very big key part in this new AI workflow. We all know that, right? And the promise was that it would help us to break some of the silos from traditional ML ops, right? Things like we have to create specific models for specific use cases, right? And in many ways, it lived up to the expectations. So more and more we see special language models being used, of course, across different use cases, right? We see the value there. I think it's even more exciting to start to see things like time series being used across different modalities. And we're seeing that you can really kind of now streamline how we actually produce these models. What I think we underestimate in many ways is the complexity behind this, right? And I think in this community, we keep hearing more and more the challenges that are behind, which is not really trivial to operate this whole workflow, right? So when you really look how this is deployed in production, we see that, first of all, it touches many personas, right? And I think this is all very familiar to you guys, but of course, it starts with things like setting the right goals. In this industry, we are way past the just prototyping experimentation, right? Every single use case starts with like what we really want to accomplish here. The cost is so high behind some of these things that from the get-go, you have to have a good clarity. What are the goals? So this, of course, involves like the business sides of the house, but then very quickly gets into things like how to prepare the right data for things like fine-tuning, right? So, which involves the data engineer, but also start to involve the platform engineer, right? Folks are actually setting up things for your actual users to run. Gets into the model development. That's where things get very interesting because model training, as we all know, it's very costly, right? Having the right data sets for the right use case is so important here. And then we start to touch other personas, right? The data scientist, ML engineer, and so on, right? Very familiar for all of you, but again, I'm just highlighting all the steps and again, the complexity that sometimes you see behind this. Then it gets even more interesting when you start to actually go to the app developer, right, which touches things like your platform engineering, the internal platform engineering, right, the way they can consume specific data sets to validate and so on. This is very familiar to many of you, but the question is, if you really are after a platform that provides coverage end-to-end, how it looks like. So what I'll show today is our point of view, IBM's and Red Hat point of view, how I actually truly believe we can build an end-to-end open source stack to give you full coverage of this end-to-end workflow. What do you see in this picture? Two sides. Left-hand side is what we use for data preprocessing and training. You see some familiar open source projects. Of course, Ray plays a big role there. It's not alone. It actually runs side by side with things like PyTorch and a few other things that I'll describe. On top of this, you see things like CodeFlare, which is a project that IBM initiated in the open from the get-go to simplify a little bit how you actually deploy KubeRay clusters, and I'll describe it a little bit more. I mentioned about PyTorch. We truly believe that PyTorch is the framework for training and tuning, so really double down on how we use PyTorch. We've been working with this community for a long time, and I'll describe some of the things that we do with them, especially in distributed training environment. And you see that these things run on top of KubeRay for Ray clusters. We do a lot of integration with both the upper layer for usability, but also how you actually deploy this on batch schedulers. We work very close with communities like Project Q, and I'll describe a little bit more. For PyTorch, this also runs as batch jobs, and here we integrate with a Kubeflow training operator. And the important piece is that these things, they coexist, right? The challenge here is that to go after that whole workflow, you have to have a platform that you're able to orchestrate all of this, right? Left-hand side is all about batch jobs. from single GPU to thousands of GPUs. And the way we kind of coordinate this is with things like Q as a batch scheduler. On the right-hand side, we don't try to reinvent the wheel. And the beauty here is that we leverage things that exist, we fill gaps, and we contribute back. We start with things like K-server at the top. This is bread and butter. We all know how to use this. IBM has been deploying K-server in production for a very, very long time. We know what is the pain, some of the contributions that we made, and so on. But we start to actually fill some gaps. For example, when it comes to fine-tuning, so important for our business, we really kind of double down on Hugging Face libraries. Use Hugging Face SFT, for example, for training, for fine-tuning. And we built on top of this some of the recipes that we need for our use cases, and all of this goes into the open. Underneath, we still rely on PyTorch. So PyTorch FSDP is actually what is driving most of our use cases, including for tuning. So when we need to go beyond single GPU, for example, for fine-tuning, PyTorch FSDP is actually what is driving. On the inference side, we do both VLLM and Hugging Face TGI. Reason why some innovations are kind of catching up one or the other. So we have plans to really converge to VLLM, like many people here in this community. We see that it's still developing, so there are some things that we need. And I'll call out a few that it's not there yet. So reason why we still have Hugging Face. There is something that you probably see in this picture that I don't know if it's familiar to all of you. Triton is not the inference server, but actually the programming language for GPUs. It's an OpenAI, open source project. Triton gives you a way to write GPU code without CUDA, which is great if you want to support different hardware accelerators. We have been experimenting with Triton, actually writing kernels for Triton for some time. To a point, just last week, we published a blog showing a completely CUDA-free set of kernels for inference, giving like full coverage. So when you look at this stack, a lot of the things that you're running underneath in terms of compute kernels, so this is the DGEM, like the matrix multiply kernels. This is, for the most part now, using Triton. Why we do this? This gives us freedom, right? In terms of porting this to other hardware accelerators. We run with NVIDIA today. We can run with AMD as well with this. And we also, of course, work on some other accelerators as well. What you see underneath, I don't know how familiar things like Kubernetes DRA is to you guys. But again, I mean, it's all about how you really make GPUs a first-class citizen in Kubernetes, how we actually fraction GPUs. There are a lot of proprietary tools in the community. DRA, which stands for Dynamic Resource Allocation, is something that is trying to actually bring a Kubernetes native support for fractioning. This is still forming the community, so IBM Red Hat, we are very much engaged. I'll call out a few things that we do, but it's still forming. A reason why we created this project called Instant Slice, and there'll be some QR codes in a little bit so you guys can actually get pointers. This is an open source project that we have that allows you to get like a fractions of GPUs for Kubernetes, right? So you don't have to change your VLLM code or your Hugging Face code. You can actually instantiate a fraction of a GPU on Kubernetes, right? And you see how all of this comes together in some use cases. We believe that open source is really a two-way street, meaning that we leverage these things, but we contribute back. We've been working with the Ray community for a very long time, actually. In this community, a long time is probably like 2 or 3 years, right? But we've been engaged from early days of Ray. And I call out some of the things that we've been doing, right? Project CodeFly is the very first thing that we put out there, again, as an SDK to stand up Ray clusters through KubeRay. You see a video of this in action in a little bit. More recently, we've been doing integration with Kubeflow pipelines, because again, our pipelines are mixing some different frameworks. So we want to make this coexist. So if you need to spin up KubeRay through Kubeflow pipelines, that's something that you actually work with the community now. I'll highlight Data Prep Kit. You might have heard about this. There were a few talks through Summit, and I think at our booth, there was also some demo for this. So data prep kit, as you probably heard, runs on top of Ray. And I'll also give you a little bit of highlights here. At the bottom, KubeRay is how we deployed Ray. Okay, so we've been doing a lot of the automation to deploy KubeRay clusters, right, through CodeFlow SDK and so on. PyTorch is a very, very big one for us as well. We've been working very closely with this community for over a year and a half now. IBM is part of the governing board of the PyTorch project in Linux Foundation, along with some of the other names you see on the chart. What we do there, especially distributed training. So if you heard about the fully sharded data parallel API, this is something that IBM has been contributing for quite some time. The beauty here is that we are seeing 30% throughput improvement over state of the art. So if you read our blogs, which I highly recommend, you see our journey over a year and a half adding some support to do highly scalable distributed training, okay? And all of these things actually at the core. You can use this at different levels, right? So there are abstractions on top. But when it comes to actually doing the parallelization algorithm, fully shared data parallel in PyTorch is what we believe is the standard, right? Torch compile is something that we also have been highly involved. We actually have some very good position in this community, driving some of the directions of Torch compile. And finally, Hugging Face. That's something that I mentioned before. We are actually contributing things like speculative decoding to Hugging Face TGI. And this is also coming to VLLM. We are seeing 2 to 4x improvement in latency for inference with innovations like this. And finally, Kubernetes. As I mentioned, Kubernetes is the platform for us. With clients and partners, it's very clear that Kubernetes is the way to run and operate AI platforms. Not something new for you guys, but it's amazing how Kubernetes was not really designed for this type of applications, right? So there are many gaps, and actually hoping we're closing some of these gaps. A big one is actually batch scheduling, right? There is a project called Project Q that is a batch scheduler quota manager for Kubernetes. IBM, we actually contributed a big chunk of what is in Q today, especially when you connect it to external frameworks. One of them is, of course, Ray, but also PyTorch and others. I talked about the array, dynamic resource allocation. Again, something that is coming to Kubernetes, not fully formed yet. But again, we truly believe that a vendor-agnostic approach for fraction is the way to go in this community, and the array in Kubernetes is the answer, reason why we're deeply involved. All of this happened through like a few of these working groups in Kubernetes in which we are highly involved. Finally, at the bottom, training operator is how we deploy very large PyTorch native jobs. And we have one of the largest deployments of the training operator in the industry right now. And actually, I'll give you a sense of this, right? To give you a sense. This is one of the environments that you run. So when I share this stack, we drink our own champagne, meaning that we actually, this is what we use internally and what we sell through OpenShift AI to our clients, okay? And how we also build Watson X, our flagship catalog of AI on top. What you see in this slide is basically how we run this on IBM Vela supercomputer. This is a cloud-native supercomputer, meaning that we run this on VMs, right, plus Kubernetes on top, and this goes across thousands of GPUs. The number changes a bit, but again, think of this as a couple of thousands of GPUs. This is not the only environment where we run things. We have also other environments. There's the entire life cycle of GenAI, right? We do some of the data preprocessing here, model training, some of the tuning, and some inference as well. So you can see anything from like a single GPU job all the way to hundreds of GPU jobs. All of these coexist on the same platform. Of course, you need to do things like a preemption, quota management, right, and all of these things, which we do through the scheduler that I described, right? This has been in production over 2.5 years now. Tons of experience actually running end-to-end. I can share offline if you guys are interested, but our journey was from like early days of Ray through PyTorch and Ray to like some of the things that you do Kubernetes. So when I say, hey, it takes like a few moving parts, this is again through first-hand experience really operating this platform at scale. This is how it looks like in terms of how all of this comes together, okay? So I describe what is in the middle of this picture, which is, of course, the open source tooling, right? And you can think of this much like what Red Hat does for Linux and Kubernetes, where we get behind open source projects, and then we package and support. So if you need enterprise-ready Linux, you get RHEL Linux, for example. If you need enterprise-level Kubernetes, there is OpenShift. OpenShift AI is the same for the stack that I described, right? It's a way to get best-in-class open source supported. So you actually call Red Hat, not, I don't know, one of the community developers, right? We believe this so much that we build our offering, which is called Watson X, on top of this. Watson X is more like opinionated, right, version of the offering, meaning that you have things like guardrails and endpoint, right, workflows, data governance, and all these things. Watson X is built on top of OpenShift AI, right? So just so you guys understand. And at the bottom, of course, is our hybrid approach, right? To build this platform in a way that you're not tied to one single cloud vendor. In fact, many of our clients run this platform on-prem, right? The same value proposition here you can get from on-prem to any cloud provider. The Vela supercomputer that I described run on IBM Cloud. We have instantiations of this running on AWS, and as I mentioned, some of the clients also run on-prem. The QR code leads you to a blog post describing every single component in this stack and how we use it. Let's talk about use cases, right? So I think by now you saw the stack. Let's see how it actually works in the field. I have two. One of them you probably heard about. This is the data prep kit. So this is interesting, right? So we've been through the journey of preparing data sets to train our models. Remember that IBM, we also have our own foundational models, right? It's quite of a journey. We had code to do some of the typical data prep process, things like deduplication, fuzzy deduplication, identification of a language, and things like that. But we decided to start from scratch in the sense that we wanted to make sure that we had code at scale that used one single platform, right? It was very easy to maintain, very easy to develop. And some of the developers are actually in the room here, so they can give you like first-hand experience as well, right? Long story short, this is not new in the community. We all going through some sort of data pre-processing, so we decided that instead of starting from scratch, we'd put this in the community so folks could reuse, right? Data prep kit is a set of data transforms, okay, implemented in Python, with Ray ports as well, so you can easily scale this in Ray, but also show that you can also run this even in laptop, just Python, or can scale even with Ray and Kubeflow pipelines. You can see sorry, there's something popping up here. You can see the URL, and I'll have a QR code next, so you actually can go there. So here's what we have, right? We cover language and code today. Support for Python, Ray, also Kubeflow pipelines. What you see on the right-hand side are the things that you have available in terms of modules or data transforms, as we call it. And you see that, again, Ray will cover all of them. So there is a Ray version for all of this. There's also integration with Kubeflow pipelines, so you can use for automation, right? We deliver these as a Jupyter notebooks that you can reuse, okay? Again, something that you guys can, instead of starting from scratch, can be reused. In fact, this is what we use to train or to prepare data to train our own models. So what you see here is just like a snapshot of what it took us to create the data to train our latest Granite model, 13B. So this is something that is also in the open. So you can see how interesting it gets, right? Start from like terabytes of data for text extraction, remove the duplicates, you get to 13 terabytes. remove hate and abuse, profane speech, for example, got 7 terabytes, and then we ended up with 2.5 trillion tokens, right? Tokenization is also something that this library provides, right? QR code actually takes you to a paper describing the whole process of data curation for this model. And at IBM, we actually love open source so much that we actually put all these models out there. So if you haven't heard about Granite family of foundation models, please check it out. It is all in Hugging Face. We have models for code, language, and also a very special one, which I'll talk about in a little bit, geospatial data. There is also time series, which is very, very interesting. We keep talking about multimodality foundation models, language dominate. I think only now I start to see the value in other domains. Time series definitely one, so you don't want to train from scratch your anomaly detection models, for example. And we also have a time series model for, a foundation model for time series that you guys can check it out. It's actually very small, very easy to deploy. Doesn't take a lot of resources. All of this in open source, the right licenses, so you can actually reuse this and share feedback with us. I'll switch to another use case. And this one is very close to me because this is with a very close partner. So we partner actually with NASA to train foundation models on geospatial data. This partnership has been going for a year and a half now. It's really like first of a kind, if you will. NASA has petabytes of satellite data that is actually public data. You can actually use this to train different models, right? And the problem here is that if, for example, you're looking for fire burn, like fire scars, right? Flooding patterns and things like that, many scientists would actually start from scratch to train models for those use cases, right? So we partnered with NASA to actually apply transformers to this type of data and to train the very first geospatial model for geospatial data, right? And the challenge was also that NASA wanted a common, consistent experience across all the environments they run. That's actually one of the key pain points they had, right? They run some of the traditional supercomputers, right? These are behind the firewalls with a tight security. They have access to public clouds, actually all of them, sometimes even with like cycles available, and also some on-prem environments, right? A couple of few. The problem for the users, right, is just like being able to produce an application that they can actually move across these different environments, right? What you see in the middle, and I'll describe in a little bit more, is like what they call managed science cloud, right? Where you can actually procure cycles, but again, if you're a user, you have to go there and learn how to deploy this on AWS. So what we did was to use OpenShift AI, what I've been describing as a common platform that go across all these environments, actually show in action. So left-hand side here is our stack as I described. Right-hand side is where actually we did a few of these steps, like a pre-training. It was all done on the Vela supercomputer that I described with hundreds to thousands of GPUs for some of these models. Models themselves, they go into an object storage, right? Then the fine-tuning happens on NASA's public cloud, right? Where we have dozens to hundreds of scientists taking this model now and fine-tuning for specific use cases, right? And then finally, inference can come back to either IBM Cloud or some of their on-prem environments, okay? I'll now actually show this in action. So what you see in this video, and it goes very fast, the 3 environments, okay? Let's start with left-hand side, and this is how it looks when you deploy this on the Vela supercomputer, right? There are a few ways actually to present this to the user. One of them is actually a Jupyter Notebook, which is, of course, very, very familiar to many, many scientists, right? And what you see in this picture is the CodeFlow SDK, for example, how you request resources, very high level, so you can just say like number of GPUs, configuration of memory, and things like that. And then you can use some of the SDK APIs, things like cluster up, and actually you set up the cluster environment for this. This is all actually triggering actions on the OpenShift cluster, so you don't have to know anything about how to deploy a pod, how to start KubeRay, and any of these things, right? I just have a PyTorch code that I need to deploy. I know how to do this on my laptop with no GPUs or single GPUs or like a workstation. I just want a way to actually run this across, say, 100 GPUs without having to learn all of this, right? So you see some of the API in action. There's some like output. So we get, for example, information when the cluster, this video is tricky sometimes. Just go back here. Just get like the output when the cluster is up, and then you can actually start to run your code, right? This will be, again, just plain PyTorch code, fully FSTP. Just went back to some of the information. Now I have my cluster ready, and we start to actually run the code, right? This, of course, like in accelerated speed, right? So you see just some of like the initial training. This will take some time, actually weeks to months, as we know. So fast forwarding, this will be done after some time. This is a small model, so you get the sense, right? Now, the beauty here is that we trained the model, okay? Now I want to fine tune the model. So what we show is that now we can deploy the very same stack on the public cloud. This is OpenShift running on the public cloud. Same experience in terms of like a Jupyter notebook. This is a fine-tuning recipe that I can distribute to the data scientists. In fact, NASA did exactly that. They run like a workshop with many scientists in geospatial area with this type of recipe. What is happening here, again, it's a bunch of pods being deployed on OpenShift, right? You don't see them. This is actually, every time I switch here to OpenShift, so it's what's actually happening underneath. And finally, this is how I actually build an application. So I fine-tune the model. I have a field that specialized to, for example, flawed patterns, right? Now I want to inference the model. So now I can actually go to the inference side of the stack, and we deploy this on an on-prem cluster, right? Same experience. Now I can actually use high-level APIs to build an application. So what you see here, it's an application that you built using some of these APIs to inference the model. So what you do, for example, just take Albany. We're in New York. IBM Research is in New York. So let's do some inference for flawed patterns in that area. So you can inference the model. We can actually go to a different location, do the same. So you get the idea, right? So it's all about how, again, you can use this model now through some sort of APIs that are very much standard, right? And you don't have to worry about, again, how you deploy some of these resources. This is like in a nutshell what we did with them. There's like a few blogs you can read about. We are very proud of this because this was the very first time that a geospatial model was trained, right? The very first one came out a year and a half ago. But we just announced 2 weeks ago the next iteration of this. This is available in Hugging Face. You can use it for any use. We do see a lot of use, for example, of course, in science, but also like insurance industry and so on, right? Highly recommend the blog if you want to see some of these in action. And that's how I conclude. Give some time for you guys to ask questions. I hope you enjoyed this. Thank you for coming again. If anyone has questions, please walk up to the mic and feel free to ask. And I'll be around as well. Okay.
I'm just curious what you found most surprising or unique about the journey you've been on in putting together today's session. Thanks.
Sure. Yeah. Thank you. I think journey is the key word, right? I think when we started this, the whole industry was just, again, understanding the complexities behind the running, especially like a cloud-native platform, right? So when you hear about some of these frameworks, amazing scaling, right? It's not what we saw firsthand when we started to scale this from, again, Ray itself to many other components, right? So I think it took like a lot of learning in terms of debugging, making it simple to debug, right? And I'm happy to see that more and more observability is something that comes up in these community, because that's where I think a lot of the pain was. We share this now with other players as well. So I think that's the beauty about open source, because some of the lessons learned, they are now captured in a way that others can benefit. But I think, again, just scaling and observability in general, how to debug things in this space was one of the biggest challenges. Things are much better now, much more like stable and scalable.
Okay, no one's coming up, so I'm going to hog the microphone.
Please do.
A lot of the focus for the last several years has been on like concerns about diversity, fairness, transparency, and equity associated with these models, making sure that they behave themselves. But increasingly in the last 6 to 12 months, there's been sort of a turn towards the potential security of these new workloads. And I'm just curious on your opinion as to, are these just yet another workload that needs, security by design, or are there unique things about this that have you concerned about bad actors, malware, injections, et cetera?
Oh, that's a very, very good question. I think something that is also very close to us, because we went from like the state where you're free to experiment, right? And there was not a lot of concern about best practice for security, because again, it's an experimentation phase. I think as an industry, we're realizing that this is actually touching now like mission critical paths, right? And there's a lot of best practices for security that was not really kind of followed. So I think in many ways, we have better ability to actually apply some of these best practices, right? Just again, running these on Kubernetes, all the compliance, the controls, all those things need to be in place. Reason why actually we are so emphatic actually running these on Kubernetes is the way to go. But number two, how you secure model itself, right? So things like model as containers, for example, that reduce some of like your risk surfers and things like that. So I think it's not fundamentally new in terms of securing the platform, but there's a lot of best practices that, again, are not fully being leveraged now that we could, right? So I think it's a mix, but security itself is, of course, it's a big pain point right now, right? Yes, so I hope I did address the question. Okay, thank you very much.